In this lecture, we're going to talk about batteries and fuel cells. We're going to get it started there. So the first one to talk about is a dry cell. These batteries they're non-rechargeable and expensive and heavy, and they corrode easily, so they're not great. And you probably don't use them typically. Inside one of these batteries, we have a carbon rod electrode right here that comes down through the center of the battery. And it's inserted into this paste right here that is composed of some manganese oxide, ammonium chloride, and zinc chloride and water. And this is really, the cathode is this kind of component right here. The cathode itself is really the carbon rod or the graphite rod. And the anode is then going to be zinc, which is going to be, here we go, around the outside here. And what's happening was we'll have our zinc being oxidized to form zinc plus 2, which is also in the paste inside the inside the battery. And then we'll have our manganese being reduced, our manganese oxide, to manganese 2O3. Batteries like this will produce a cell voltage of about 1.5 volts. But again, they don't have a lot of desirable qualities for a battery. Alkaline batteries are ones that most of us have in our households, like Energizer alkaline batteries. So these are pretty common. The electrolyte here is going to be a potassium hydroxide paste. We're still using an anode that is zinc. So we'll still see that same reaction of zinc forming zinc plus 2 as it loses 2 electrons. In this case, the cathode is manganese oxide. And I'm sorry, there is a typo in the lecture notes. It's not a brass rod. It's manganese oxide. And that manganese oxide is mixed with some coal dust, and that's our cathode. And it's here on the outside, and it's separated by this porous kind of divider from the zinc powder that has the potassium hydroxide in here. And then we have just a rod for our anode current collector. And so here we have our zinc powder on the inside which is being reduced, and our manganese outside of it that's being oxidized. Or sorry, I flipped that. Our zinc is being oxidized, and our manganese on the outside is being reduced. These have a cell voltage similar to the dry cells, 1.54 volts. And compared to the dry cell batteries, they tend to just last longer. Some are rechargeable, but that's usually pretty limited in how long their overall lifespan is. And there's less corrosion of the zinc. Too far. Nickel cadmium batteries. These are pretty interesting. So again, we're using potassium hydroxide as the electrolyte. But these go away from using zinc as the anode. Instead, it's cadmium. So we see cadmium converted into cadmium plus 2 as it's oxidized, and it loses 2 electrons. And so that cathode is actually going to be nickel coated with nickel oxide. And let's show you here. So we're going to have these layered like a jelly roll in the battery. And so here's our positive electrode right here. And then we'd have a separator here in yellow. And then we would have our negative anode, which is like a pressed powder in between our 2 separators here. And at that negative anode, we have, I'm sorry, that's our cadmium hydroxide. And at our cathode, we have nickel rather than manganese. And our nickel, which is going to also have this nickel oxide hydroxide compound as well, which will pick up the 2 electrons from our cadmium and form nickel hydroxide or nickel 2 hydroxide. So these have a lower cell voltage of 1.2 volts, but they're rechargeable. They've got a very long life and they're light. So they're pretty great for that, at least. Then we have lead acid batteries as well. So here the anode is our lead, but our cathode is also lead, but it's lead coated with lead oxide. So at the anode reaction, we see our lead is oxidized to lead sulfate, or lead +2. And at the cathode, we see our lead oxide, so this is really lead +4, pick up 2 electrons and form lead sulfate, which is lead +2. So here we're going from Pb +4 plus 2 electrons to lead +2. And here we went from lead to lead +2 at the anode. And so these cathodes and anodes are here. They're these plates, and they're inserted into dilute sulfuric acid, which is what's providing the sulfate ions that are necessary to bind with the lead. The cell voltage for these are 2.9 or 2.09 volts, and so 6 of these together makes a 12-volt battery. They're rechargeable, but they're heavy. These are the types of things you'll find in your car. So a fuel cell is a lot like a battery, but it's a battery where it's constantly adding reactants and they don't get completely used up because of that. So there's still a hydroxide electrolyte solution like in the alkaline batteries. And in this case, the anode and the cathodes are actually just inert anodes and cathodes. They're both platinum. Or platinum coated metal. And it's at the anode, we have a reaction that's taking place where our hydrogen is being converted into water. And at the cathode, we have oxygen being converted into hydroxide. And so we're constantly supplying oxygen and we're constantly supplying hydrogen into the fuel cell. And together, these mix and produce water out. And so it's combusting hydrogen to form water in a fuel cell, which it means your byproducts are really environmentally sustainable. And, you know, aside from the cathodes and anodes being platinum or some other metal coated in platinum, it's fairly benign. Now we're going to take a look at corrosion, which is the spontaneous oxidation of a metal by chemicals in the environment, and that's usually oxygen. So oxygen is a great oxidant, which means it's easy to reduce. And in even just moist conditions, so a bit of water around, oxygen has a positive reduction potential, which means it's likely to be reduced. But if you have this in acidic conditions, then, so once we change that, we see the reduction potential for oxygen becomes even more positive. So that makes it even more likely to occur. Or it's even easier to reduce oxygen is another way of thinking about it. But remember, strong or very positive reduction potentials would be a driving force for the reduction part of a redox reaction. So when iron rusts, it is undergoing corrosion. And I think this is the most common form of corrosion that we deal with in our daily lives. So first we see that the iron can, if iron is oxidized to iron +2, we have 2 of these, we could release 4 electrons. Oxygen, which would be on the other side of this redox reaction, could then be reduced to water using those 4 electrons that came from our iron right here. And so the presence of oxygen by iron can cause this redox reaction to occur. But once we have iron plus 2 around, and now it's in solution of some water, and if there's oxygen around, then the rust formation reaction takes place. Iron plus 2 and oxygen will react with water around to form iron 2 oxide, or iron 3 oxide, my apologies, or rust. And it'll have some numbers of water coordinated to it. And then you'll have this rust pile up as well. And so under these conditions, we see that electrolytes tend to promote rusting, and that's because it enhances the current flow, so it makes it easier for electrons to flow through this droplet of water. And then also under acidic conditions, we see more rusting because the lower pH means the reduction potential of oxygen becomes more positive and makes it even easier to reduce oxygen. So some ways for preventing corrosion are to reduce or to slow it down in general. One is to just coat the metal surface. So that's like painting your car to prevent it from corroding. And another method is to use a sacrificial electrode. So this is a different metal that you attach to the iron that is more reactive. And so it will act as, it will be reduced with oxygen around rather than the iron because it's easier. So you can see this when we have buried pipes or iron pipes. Moist soils, a great place for rust to occur. It acts as an electrolyte and waters around and oxygen. And so including a sacrificial anode like magnesium when building out the pipes becomes a galvanic cathodic protection system, essentially. And so the magnesium will react with the oxygen rather than the iron. You also see this on the hull of boats. And in this case, it's usually these zinc kind of like, I guess, bars of zinc that are placed all around the hull. And they act as a sacrificial anode and will corrode away instead of the iron of the hull on the boat. Now let's take a look at electrolysis. Not too far. So electrolysis is making a non-spontaneous redox reaction occur. So an electrolytic cell will actually use electrical energy to do that. So it's basically the opposite of a voltaic cell. In a voltaic cell, we expect to have an anode here where electrons will leave as it is oxidized to the cathode where it'll reduce the cathode electrolytes. And so we see these electrons travel from anode to cathode. And in the example we looked at previously with zinc and copper, we had a voltaic cell potential of 1.1. An electrolytic cell under these same conditions would instead be applying a current. So that way electrons traveled from the copper to the zinc. And you would have to apply 1.1 volts. Or you could think of this as switching, if you had switched your cathode and anode, we saw a negative potential, a negative 1.1 if you did this in lab, if you just switch your alligator clips. And that's really telling you what is the voltage that needs to be applied for this to go in the reverse reaction, or the non-spontaneous direction. In general, electrical energy needs to be a direct current supplied to the system. And so you would attach the positive terminal to the anode and the negative terminal to the cathode. And then we will see that if you were using inert electrodes, that cations and electrolytes in the electrolyte would be attracted to that inert cathode, and they would pick up electrons from it to be reduced, and then anions would be attracted to the anode to release electrons to be oxidized. Some electrolysis reactions are going to require more voltage than you would predict. So in the copper zinc example in the previous slide, we would expect we would need to apply 1.1 volts. And it might be more than that. And that's what we call over voltage. And it's it's much like the actual cell potential isn't 1.1 volts at non-standard conditions. More voltage is typically required to actually drive an electrolytic cell. In general, when trying to decide which half reactions are going to lead, what combination of half reactions will occur during or in an electrolytic cell, you're going to want to look for the combination that leads to the least negative value for the cell potential when you run, when you calculate it from the cathode and the anode. One I think the most interesting reactions that we can look at with electrolysis is splitting water. So the spontaneous reaction that happens with hydrogen and oxygen is its combustion to form water right here. And we take advantage of this in fuel cells. Now the opposite of this is non-spontaneous. That is splitting water into hydrogen and oxygen gas. And this requires energy to drive this reaction. And you can do that by applying a current across water. And if you do that, and we've got an example of a setup right here for doing it, if you apply a current by putting in an inert anode and an inert cathode electrode into water, you'll start to see oxygen collect above the anode and hydrogen gas collect above the cathode. And you'll notice you're collecting twice as much hydrogen gas. And that's coming from this 2 coefficient here in our balanced chemical reaction. And this is water with, it's acidic water, so it has some sulfuric acid in it. To improve the conditions under which oxygen will be reduced, to do it at its, give it a higher reduction potential. And so at the anode, we have water right here, and this is similar to our corrosion example. We have water splitting up into oxygen plus hydronium ions, or H+, and 4 electrons. And at the cathode end, where we're producing hydrogen gas, we have water reacting with 2 electrons to form hydrogen gas and hydroxide. And there's a lot of really interesting research out there into what kind of electrolytes to add to water to improve the amount of voltage that needs to be applied to split water into oxygen and hydrogen gas. Because if we can reduce that potential, then we can more efficiently split water into hydrogen and oxygen, and then use those components in fuel cells and combust hydrogen for energy. And this becomes part of the picture of a kind of a renewable energy source, that if we can take energy from the sun and run it as a direct current through water with the right electrolyte solution, we can efficiently produce oxygen and hydrogen gas that can be stored and then pumped into a fuel cell to be used for energy later. This reaction right here, this electrolysis reaction, is what is happening in photosynthesis too. This is how plants are generating energy. And so it's And that is kind of where the inspiration for all the research going into electrolysis of water as a fuel source has come from.